Hello everybody, welcome back. So, today's about logs, but before that, I want to illustrate a couple of quick points for you. So you know how we have the compound interest formula and the continuously compounded interest formula? Well, here I've managed to graph both of them. Notice how this one has a bunch of lines that are horizontal. What this means is at this point, at the front of the line, interest gets compounded. But it doesn't get compounded again until you hit the next point of compounding, which would be up here, in which case the interest jumps up. So you can easily see that for interest-wise, if you are paying, you'd much rather go with compounded a certain period of time, because if you start paying here, well, all this interest hasn't accumulated yet. Now the other graph here is using the continuously compounded, which, if you look as you go up, you notice that there's more and more of a difference between the two lines, even at the starting points. But we have this n here, which I have set up to calculate for how often it's compounded. So if you look at 2, well, it's getting closer, closer, and it keeps going, gets closer and closer to the continuously compounded line, which, if you zoom out a lot, even way up here, there's not much of a difference. And if you go up to 100 times compounded per year, yeah, there's very little difference between these two lines. So continuously compounded and compounded at certain periods of time, there might be a little bit of difference, but in general, there's not going to be too much difference. So I want to start off with that. Now, over to logs. So logarithms, which the main point of them is finding the x, which is already in the exponent. So if you're solving for the inverse, it's finding the y. So let's say we have a nice, simple, continuously compounded formula. So we have $1 put in at the start with a 100% interest rate. I know you probably would want that for a savings account, not for a loan. Well, first step of finding the inverse, put the y there. Second step, switch the two. Well, you can't really go further than this without a log, because you need to know what that exponent is such that e to that exponent is equal to t, which that's where logarithms come in, which whenever we have a log, you should be reading it log base, whatever it is, so natural log, so ln is base e, the log base e of t equals y. Now, what this is saying is e to the exponent of y equals t. So it's the same statement we've had before. So whenever you're taking the natural log of something, you're looking for an exponent. And of course, this is going to be a function. So make sure that final step, p inverse of t, is equal to the natural log of t. It's a p, not a f, because our original function was p of t. So what are the logs? Well, the following two statements are equivalent. A equals b to the c is the same statement as c is equal to log base b of a. So this bottom statement is saying b raised to the power c equals a. So these two statements are saying the same thing. Keep that in mind whenever you're using logs. Further, whenever you introduce logs into a situation, you need to make sure to specify what the base is. If you do not, then it's going to be assumed to be log 10. All right? Further, if you are taking the log of both sides of the equation, which is completely allowed, you have to make sure you're taking the log of the entire side. So notice here how log has parentheses with it, because it's basically a function of its own, like f of x, or something like that. So everything has to go on the inside. So you'll be seeing more examples of this in class, and I will see you there. Good night.